My name is Caro, and I will present them the project titled Modeling and Simulation of Gold Nanoparticle for the purpose of studying surface interaction with cysteine. In recent years, nanomaterials have been widely used for a variety of applications in material science, computer, medicines, engineering, among others. And gold nanoparticles have been extensively employed in nanotechnological applications, especially in biomedicine, cosmetics, and pharmaceuticals. The surface functionalization of the gold nanoparticles is a chemical process in which functional groups are added to facilitate the integration of different molecules in biomedical applications. The surface of the gold nanoparticle can be coated with different ligands such as antibodies, genetic material, drugs, carbohydrates, amino acid, and lipid layers. Functionalized gold nanoparticles present an improvement in their chemical stability and electrical properties, which has made them an object of study for drug delivery, nanosensors, tumor markets, etc. Cysteine is a non-essential sulfur-containing amino acid in humans, which is related to cysteine. Cysteine is important for protein synthesis, detoxification, and metabolic processes. Recently, it has been demonstrated that non-essential amino acids like cysteine and lysine have an affinity for forming complexes with metals such as gold and silver. This affinity is due to the R group of each amino acid, which in case of the cysteine is the group thiol. This exhibits a high electronegativity. Cysteine has a strong affinity for gold, which is why it's being used to coat gold nanoparticles. This amino acid can combine with other molecules through covalent bonds and amides. This makes the gold nanoparticles similar to other negatively charged materials, which helps scientists better understand the interaction between the gold nanoparticles and the amino acid cysteine. Cysteine functionalized gold nanoparticles, such as the one we can see in the figure number 2, have been widely used for members of the scientific community in various areas and applications such as colorimetric sensors, regenerative medicine, biosensors, and others. This project main objective is to evaluate the binding properties of gold nanoparticles by modeling and simulation, and it's achievable throughout 3 specific objects. Number 1, to generate the modeling and simulation process of the gold nanoparticle using Biomaterial Studio 2022 software. Then, to propose a biomolecule that interacts with the model nanoparticle, in this case it's the cysteine, and to measure the surface energy of the gold nanoparticle interacting with the proposed biomolecule of interest. The methodology for this project consists of 5 parts. Number 1, modeling of the gold nanoparticle using Biomaterial Studio 2020 software, followed by the study of the binding properties of the amino acid cysteine. Then, modeling the cysteine using Biomaterial Studio 2020 software, followed by simulation of the gold nanoparticle and cysteine interaction, and finally the measurement of the surface energy resulting from the interaction of the gold nanoparticle and the cysteine. Figure number 3 represents the results of the modeling process for the gold nanoparticle. We have the gold nanoparticle with radius of 10 angstrom, which is equivalent to 1 nanometer, composed of 249 atoms with a value of atomic number of 197. On figure number 4, we can see the representation of the amino acid cysteine. We can see the structure of the L-cysteine, which is composed by a carboxyl group, an amino group, and the thiol group. L-cysteine also exhibits chelantic properties, which means it has a high affinity for metals. For the gold nanoparticle cysteine interaction, the calculated results reveal the presence, first of all, of covalent bonds between the thiol group and the gold nanoparticle. We have a energy regime between minus 387.36 kilocalories mole to minus 387.675 kilocalories mole. The negative sign indicates that the energy is released rather than absorbed during the chemical reaction and the physical process. The decreased energy suggests that the interaction between the gold nanoparticle and the cysteine has that energy to release within the system, and this type of reaction is known as an exothermic reaction. The decrease in the potential energy could result from a beneficial thermodynamic transformation in the system, such as the formation of the stronger bonds and the reduced entropy. The entropy is reduced because of the reaccommodation of the atoms during the interaction. The reduction in potential energy indicates that the reaction between the gold nanoparticle and the cysteine is beneficial and leads to a stable interaction between the components of the system. Conclusion. The research found that the thiol group of the cysteine and the surface of the gold nanoparticle form a covalent link which mediates the interaction between the gold nanoparticle and the amino acid. Because of the thiol's group affinity for metals, covalent bonds are used to generate this strong and stable link. These covalent bonds easily form and give out energy, providing that the process is exothermic. The interface bond energy presents ranges from minus 387.36 kilocalories mole to minus 387.675 kilocalories mole. These results indicate the energy released during the process and confirming that the reaction is exothermic. This may be caused by the spatial arrangement of the atoms that form stronger bonds and have better stability for the long-term life of our system. Generally speaking, these discoveries offer knowledge on the structure and stability of the interaction between the gold nanoparticles and cysteine, which is important for the application in a variety of industries such as nanotechnology, medicine, pharmaceutics, engineering, etc.